Hi everyone. In this video, I'm going to show you a very important topic that applies to concentration of solutions. When we make solutions, we make them, of course, to a selected concentration, a concentration that we desire. But we can change concentration of a solution because we may be working with different applications requiring different concentrations. So the way we change the concentration is we can make the concentration higher or lower. If I make my concentration higher, what should I do to make a solution more concentrated? The most obvious way of doing that is we can add more solute to the solution, and this way we increase the concentration of the solute. And the other method, which would be to evaporate the solvent. This works best for situations when you're dealing with non-volatile solute in a solvent, like salt dissolved in water. The solvent being water, you can evaporate the solution. So if you have a solution of certain concentration of salt, these tiny particles are salt particles or ions in the solution. And if you let this solvent evaporate, you are going to have, of course, less volume with the same amount of solute ions, particles in the solution. So this would be more concentrated. And this method is not very practical because it takes energy and time, particularly time, if you don't want to put energy into it, to evaporate the solvent. So it's best to simply add more solute, and the first method is more practical. So to make a solution more concentrated, we typically add more solute. Okay. Or we could start over and make a new solution of more concentrated solute. But the more applicable process that we do, we tend to follow this in laboratory, in practice, is that we go through a process that's called dilution. Dilution means to add solvent. The amount of solute does not change. And if I add more solvent, what do you think is going to happen to the concentration? So let's go ahead and see what happens in terms of the equation. Molarity is, and let's work with molarity. Capital M is molarity, units of moles per liter. Moles of solute per liter of solution. Please remember these descriptions of these units. And the numerator is mole of solute. The denominator is volume of solution in liters. So if I add more solvent, your denominator is going to increase, so volume will increase. The number of moles do not change, numerator is constant, and if you increase the denominator, what's going to happen to molarity? Molarity will go down. So this is the process that we call dilution, and dilution is used to start with a more concentrated solution, and you prepare a more dilute or less concentrated solution. The more concentrated solution is called stock solution. The stock solution is what we often store, and this is very practical because you don't want to buy a solution that's less concentrated. And let's say if it's a water-based solution, you're paying for shipping and you're getting a solution that's mostly water, and it's going to cost a lot more money than buying something that's more concentrated, and then you dilute it down. So if you start with a concentrated solution, which is called stock solution, and you add water to it, let's say we work with common water-based solutions, you're going to make more dilute solution. And the point of this is that the more dilute solution is made to the concentration that I want. So here you can see in a diagram that if you take a certain volume of more concentrated solution, and let's say that's water-based, and you have this solution called stock solution, it's more concentrated, and these are solute particles. We call it stock solution. And then you take a predictable, a known quantity of the stock solution, and you add it to another container. It could be a set volume container. We often use this method. We use these glassware that's called volumetric flask, and these flasks come in different sizes. And let's say I want only 100 ml of a more dilute solution. This is typically a very precise volume, known to 4 sig fig. You transfer a portion of this into this volumetric flask. Let's call it vol flask. And we use glassware that's often pipette. Most precise transfer glassware is a pipette of different sizes. Or we could use a graduated cylinder, which is not as precise, but that also works if the concentration doesn't have to be so precise accurate. So we use a pipette or a graduated cylinder and we transfer a known volume. So then the known volume gets to be put inside of this volumetric flask. This is the same concentrated solution. And then I just simply add water. So let's say to prepare this, now you add your solvent water. So now you have a more dilute solution. So water gets added to this. So let me just mark it with this here. So this would be your solution now. And this would be the original solution. And I'm just going to color code it for you. So this is more concentrated. So it's darker color. And then if you make a more dilute solution, it is typically, if it's a colored solution, it's going to be a more faint color because you're adding more water to it. Okay. So this process is going to work in this way in terms of calculation. And that's what I want to get at. The calculation part is very important because we want to be able to prepare a predictable quantity of solution. So what we do here is if you look at just this solution inside the volumetric flasks, we can say the number of mole of solute before addition of water is the same thing as the number of mole of solute after addition of water. I think you all agree with this statement because you're only adding water. So when I took a certain portion of the stock solution and I added it to this volumetric flask, I brought in certain number of moles of solute, but now my moles of solute is just distributed over to a larger volume. And so they're taking up more space, but it's the same number of moles. The moles before and after are the same. The state before is state 1, the state after is state 2. So if I solve my molarity equation, which is number of moles over volume, and if I solve it for before and after, I'm going to transfer it here so that my before and after are in the same location. So molarity is going to be different after. So this would be M1, V1, M2, V2. The number of moles, as I just showed you, is the same. So if you solve this equation, N is equal to M1 times V1, and N also is equal to M2 times V2. This is a simple math situation where you can say X is equal to A, and then you can say Y is equal to A. Because these two quantities are equal to the same A, we can conclude that X is equal to Y. So now I'm going to take the right sides and make them equal to each other. So the important dilution equation in terms of molarity is M1V1 is equal to M2V2. This is a very important equation to memorize and understand. And M2 being the final concentration is what we often try to calculate. So if you solve this equation for M2, it would be M1 times V1 over V2. And if you rearrange the equation, it becomes M2 is equal to M1 times V1 over V2. The V2, of course, is the final volume or the total volume after you make your dilution. Your V1 is your initial volume. Let me just show them on the diagram. With the pipette, this is what we establish our V1. Okay. And because you are taking the solution of the stock, this will be M1. The concentration, whether you take any volume, 5 ml, 10 ml, 20 ml, it has the same concentration. We call M1. M1 is the initial concentration. And then here, of course, we have a V2. The volume has increased, say to 100 ml in this case, and the concentration is now different. So M2 is more dilute. We just talked about it, that if you add more water, you go from a concentrated solution to a more dilute solution. So these are the principles of dilution equation, M1V1 equals M2V2. And I'm going to give you an example so that you can solve this and put it into a perspective for yourself and see how we apply this. So calculate final concentration in molarity when 12.5 milliliter of 11 molarity HCl solution is diluted to 500 milliliter. So here's a basic problem that you're solving for M2. So let's go ahead and label. The final concentration is my M2, and the 12.5 is my V1. The 11 molarity is my M1. And the M1, or this initial solution, is my stock solution. And what's 500 ml? It's your V2. It's your final volume. So you can see that there's only one variable here, and that's M2. So you can solve it as M2 is equal to, well, write the equation the way we wrote it. So M1 V1 is equal to M2 V2. So M2 is equal to M1 V1 divided by V2. My M1 is 11 molarity. My V1 is 12.5 milliliter. And my V2 is 500 milliliter. Notice that as long as you have the same volume units in the numerator and denominator, they cancel. So you don't need to convert this to liters or anything. As long as it's matching units, it works. So please note that it would be a waste of time to convert my volumes to liters because you don't need to. You just use milliliters because milliliter and milliliter cancel away and your answer will be molarity. So please take out your calculator and solve this. 11 times 12.5 divided by 500. That would be 0.275. And it happens to be the correct sig fig here because 3 sig fig of molarity, 11 molar. This number here is 3 sig fig. And that's the together with 12.5 is also 3 sig fig is the lowest. And this would be 3 sig fig. So we went from a concentration that was 11 molarity of the stock solution. We now got a much lower concentration. And the reason being that we've diluted it to a much larger volume. So we added a lot of water in that process. We went from 12.5 milliliters to all the way to 500. So lots of water, over 480 ml of water was added to achieve this concentration. So this is a predictable process by knowing the initial volume and final volume. And of course, the initial concentration of the stock solution, I can calculate my final concentration. And you don't have to just always solve for M1. There are 4 variables here, and you can solve for any of them. Knowing any 3 variables, you can solve for the 4th. Okay, so this is just happens to be a common way of doing it. And there is one more way that, another way of expressing what we just did that I kind of referred to it, but I want to mention this in more detail. So I wrote the equation also in this way above. And so my V1 was 12.5. My V2 was 500. So this is a practical way of this ratio being called a dilution factor. So you are multiplying your stock solution by a dilution factor, which in this case, of course, is less than 1. You're dividing 12.5 by 500. The numerator is less than the denominator, so the ratio is less than 1. The factor 12.5 divided by 500 is 0.025. So my dilution factor is 0.025. And this also is useful in the way that you can specify any ratios that will achieve the same thing. In other words, 25 over 1,000 is 0.025. Or you could do 2.5 over 100 milliliter. Notice I can move the decimal to the left or to the right. So 25 over 1,000, it's the same ratio of 0.025 as 2.5 over 100. So you could take 2.5 ml of the initial stock solution of 11 molarity and dilute it to 100, and you can get the same concentration this way too. So these are all produce the same thing. And of course, in this way, in the problem that I just had was 12.5 over 100. These are all the same ratio. So why is this important? Because it really depends on how much volume we want. If I want 500 ml of the dilute solution, I need 12.5 ml of the concentrated to pour into my volumetric flask and then dilute. If I need 100 ml, maybe I don't need so much. Maybe I don't need 500. Why waste it? I only take 2.5 milliliters of the stock solution and dilute 200. Or I might need a lot more. Then I take 1,000 as a basis of total volume. And in that case, I need 25 ml to 1,000. So once you know your dilution factor, it's an important thing because you know then what factor to use to achieve the same dilution. And you also talk about this factor. It's a very convenient way to talk about it. So a factor of 0.025. Okay. So I wish you were here and I could say any questions, but please, if anything is not clear, go back to the beginning of the video and start to play back. You may have to watch this several times to get the idea. This is a very practical idea in the laboratory, and your textbook also gets into dilution as well. So I'm going to give you one more problem, and you do this problem on your own. Pause the video and calculate what I'm asking you to calculate. Okay. So let's go ahead and now say calculate initial volume necessary from a 0.250 molarity H2SO4 solution in order to prepare 350 milliliters of, let's keep it to 3 sig fig, let's say 0.110 molarity H2SO4 solution. So what is the initial volume that you have to take from the 0.250 molarity sulfuric acid solution? So this solution obviously is my stock solution, is my more concentrated solution. And you're preparing 350 ml of 0.10 molarity sulfuric acid. So this would be your, please identify the variables and proceed to solve. So I'm going to have you pause the video and work on it. And I'm just going to continue on. And after you pause the video, check your answers with my answers. So I'm going to continue, but you should give yourself like a minute or two to solve this. So here is the answer. So stock solution, this is my M1, and my M2 is my dilute solution, my V2 is my final volume, and this initial volume that they want me to figure out is V1. And they don't specify units. The easiest unit is to just work with milliliters because your V2 is in milliliters. So simply M1 V1 is equal to M2 V2, my famous dilution equation, and you're solving for V1. So V1 is equal to M2 V2 over M1. This doesn't get into that dilution factor because you're not solving for final molarity, you're solving for initial volume. So my M2 is 0.110 molarity. Always get into the habit of writing the units of next to everything, because units provide a good method for you to check your answers, because I can see if my units are consistent or if they cancel away or anything like that. So I always encourage you to do that. And this would be, of course, a volume that be far less than 350 ml. So let's go ahead and do that. 0.110 times 350 divided by 0.25. This gives me 154 milliliter. So I need to take 154 milliliter of the stock solution to achieve this dilution and create a less concentrated solution. So that's it. This establishes the basic idea behind dilution. So please review this section in your textbook and solve more problems if you need to gain better understanding of it. But I encourage you to watch the video over again and get the concepts. This particular concept that I went over here is very important right here. This is the basis for getting this dilution equation of M1V1 equals M2V2. Okay, that's it.